Swayam Prabha. Digital India. Educated India.
So last class I have discussed that if we have one variable, then how we will get the Fourier series, and then from there how we will get the Fourier spectrum. Now today I will discuss a few more example problems where I will discuss that how we will get the response of different condition that I have already discussed in my previous lectures. Now first problem that I will discuss, that if we have one suppose one single degree of freedom system where this is simple one mass whose weight is 50 kilonewton. Weight of the mass, weight of this system whose weight is 50 kilonewton. And if we apply one static horizontal force of 25 kilonewton, so we will get a deflection of 1.3 millimeter. So this is a static force we apply in a weight of 50 kilonewton, I will get a deflection. So let's find the response of this system. So if we know this is the weight, and then we know the mass will be weight by g, and if I take that g is equal to 10, then we can get that this will be 50 into 10 to the power 3 in terms of Newton divided by g 10, then we will get 50 into 10 to the power 2 kg. Okay. Now what will be the K? K is the stiffness. What will be the K? Stiffness will be the force divided by the deflection, and force is 25 kilonewton, you convert it to Newton, divided by deflection is 1.3 millimeter, so convert it to meter minus 3. So this will be, stiffness will be 19.23 into 10 to the power 6 Newton per meter. So this is the stiffness of the system. Now what is natural circular frequency? What is natural circular frequency? That you know that omega 0 will be root over k by m. So k is your 19.23 into 10 to the power 6 divided by 50 into 10 to the power 2. This is k by m. K is 19.23 10 to the power 6 divided, this is 50 into 10 to the power 2 kg. So this will be 62 radian per second. So omega 0 will be 62 radian per second. Now your natural time period, so natural time period T0, that will be 2 pi omega 0. So that will be 2 pi by 62. So this will be 0.1 second. So this will be 0.1 second. Okay. So this will be 0.1 second, and then natural frequency. Natural frequency F0, that will be omega 0 by 2 pi, because 1 by T0, that will be omega 0 by 2 pi. So omega 0 is 62 2 pi. So this will be around 9.87 or 10 hertz. So natural frequency of the system is 10 hertz, natural time period or natural period is 0.1 second. Now we have to determine the response of this system. Now it is which type of system? It is which type of system, because we have not applied initial velocity or initial any acceleration we have not applied. So, but this force that we have applied, that can be with some initial velocity, without some initial velocity. So it is without any initial velocity. So if that is the case, so now what will be my initial condition? That without any initial velocity, so this is 0. So without any initial velocity, without initial velocity. Now, if it is without any initial velocity, then we have to put that value. But here now with any initial velocity, then we have to put that value. But here it is now without any initial velocity. But there will be a deflection, initial deflection. What is that value? That value is 1.3 millimeter or 1.3 into 10 to the power minus 3 meter. Okay, so now it is undamped free vibration case, the first case that I have discussed in my previous lecture when I discussed about the response of single degrees of freedom system. So now this is the case of undamped free vibration case. Okay, undamped free vibration case. What is the response? Ut, I have already given that solution. That will be u0 dot omega 0 sine omega 0 t plus u dot or u0 cos omega 0 t. That is the response, that is the solution that I have given. Now here you know that this part will be 0 because u dot 0 is 0. So it will be only u0 cos omega 0 t, and u0 is what? 0.13. This is point in terms of centimeter. If I write that it is in terms of centimeter, 0.13 in terms of centimeter. If you write in terms of millimeter, it will be 1.3, and if you write in terms of meter, it will be 1.3 into 10 to the power minus 3. So this will be cos 62t, because omega 0 is 62 radian per second, 62t. So now here I can write that this can be 1, cos 0 can be, maximum can be 1. If I take the u modulus of u max, then it will be 0.13 centimeter. Okay. Now if I draw the plot, this is t second and this will be ut. So it will start from, if it is cos 0, if it is t equal to 0, it will be 0.13. Okay, like this. So now what is the value? So this will be plus 0.13 centimeter and this will be minus 0.13 centimeter. Okay. Now this is 0, so this value will be how much? The value will be equals to 0.05 second and this will be 0.1 second. So similarly this will be around 0.15 second. So this will be 0.2 second and so on. So here the maximum displacement, my maximum displacement is how much? 0.13 centimeter. So that is the maximum displacement of this, the problem that I have taken, corresponding to your T0 value is 0.1. So if we have a natural time period is 0.01 second, so in such case your displacement will be 0.13 centimeter. Now if you change the stiffness of the system, if you change the stiffness of the system, then the natural circular frequency will change, your natural time period will change. Then if you change the stiffness, then if you apply the same amount of load, then your deformation will also change. Okay, so then this maximum deformation will also change. So that means if you change your stiffness, then this natural time period and the deflection, everything will change. Okay, so now the same problem, now if I use another condition and if I apply base acceleration, the same problem, if I apply the base acceleration, the same problem, but we are apply a base acceleration which is harmonic. So we are apply a base acceleration, harmonic base acceleration of 0.3 g. Okay, at a frequency of 3 Hz. So this is the loading frequency or that base acceleration that we are applying. So now this expression, so this will be expression will be that m double dot plus cu dot plus ku equal to minus mub dot. Okay, so that expression I have already given to you in my previous lecture. So if I apply a base acceleration, then this will be expression. So that means now your u dot b base acceleration, this is a harmonic base acceleration with 3g acceleration, harmonic, that means the sign, and it has a frequency of 3. So this will be your omega t, omega bar t. Omega is I can write this will be 0.3 g in terms of now omega. You know that omega bar is equal to 2 pi f. Okay, this omega bar is 2 pi f because your frequency is equal to omega bar by 2 pi, or I can say the time period is equal to 2 pi by omega bar. So frequency is equal to 1 by t. So your frequency will be omega bar by 2 pi. So omega bar will be 2 pi f. So omega bar will be, this will be your sine 2 pi f t. Now this f is equal to 3 Hz. So this will be 0.3 G sine 6 pi t. Okay. So this is your UB dot, because this is your double dot, because this is the acceleration. This will be UB double dot because this is the base acceleration. Okay. Now that means this is equivalent to a load of QT that is equal to minus MUB double dot. That is equivalent this load, and M value is how much? M value I have taken that your M value is, how much is the M value here? Because here you know that if I put M value will be your sine 6 pi, and here this will be minus 15,000 sine 6 pi t. Now how this 15,000 is coming? Because here this your M is how much? M is given W by G, and W was given your 50 kilonewton, and M we got 50 into 10 to the power 2 kg. Okay, now 50 into 10 to the power 2 kg, that is the M, into 0.3 into G. So that means this term is actually 50 into 10 to the power 2 into 0.3 into 10. Okay, into 10. So this will be 1500. So this is the load which is applying here. This is the load which is applying here. And so now it is which type of case it is. This is which type of case. This is damping is not considered. So this will be undamped forced vibration. Because we have applied a equivalent force which is minus MB into UB double dot. So that is forced vibration case. So forced vibration case, UT expression that I have given. So that UT expression is U dot omega 0 minus Q0 beta K into 1 minus beta square into sine omega 0 t plus U dot cos omega 0 t. This expression I have already given in my previous lectures when I discuss about the response of undamped force vibration. So plus Q0 by K 1 minus beta square sine omega bar t, that is the frequency of the force. In terms of this frequency, that omega bar is a natural circular frequency or the speed of the force that is applied. Now here the same initial conditions we will consider, that U dot is equal to 0, okay, and here we are applying that U0 equal to also 0. Why? Because in previous case we applied that U0 is equal to 0.13 centimeter. But here the condition is that I am applying the base shear of the same system, but system is stationary. It is not initially, there is no deformation and then no velocity. That means when in the first problem that load is applied, that condition we got the response. Static load was applied, got the deformation, but static load was applied without any initial velocity. So that it is applied and so we got the response. But here the same system, now the base shear is applied but without any initial deformation and the velocity. Clear? So that's why both u dot 0 and u 0 is 0, u dot 0 is 0, u 0 is also 0. But you can apply some initial, different initial conditions also. So if this is the case, then I will get this part will be 0, this part will be 0. So this will be minus q0 beta okay, and if I take q0 by k common, then this will be 1 by 1 minus beta square also common, then I will get sine omega bar t minus beta sine omega 0 t. Okay, where is beta is tuning ratio? I have already discussed. It will be omega bar by omega 0. So omega bar is how much? Omega bar is, this is 3, so 6 pi, omega 0 is 62 pi, so 62, so this will be 0.3. So tuning ratio will be 0.3. Now if I put this value, this will be, now this force is basically, now here 1500 will be Q0, here Q0 will be minus 1500. Okay, so Q0 will be minus 1500 because that is basically Q0 sine omega t or omega bar t. So this is 1500 minus 1500. So I can put here minus 1500, 15,000, sorry, minus 15,000, and then this k is 19.23 into 10 to the power 6, 1 by 1 minus 0.3 square, then sine 6 pi t, sine 6 pi t, this is sine 6 pi t minus 0.3 sine 62t. Or if I further simplify that ut will be equal to 8.57 into 10 to the power minus 4 into sine 6 pi t minus 0.3 sine 62t. Okay. So this is my final expression of the problem that I have taken. So now from this expression you have the expression. Now you can plot the response one your t by ut. So if I plot it, this is t, this will be ut, and at different t you get the ut value. Now you have only unknown is t, and then if you put the different t value, then you will get the ut, and finally you will get this type of response and so on. So it is the same maximum value. So from here also you will get what is the maximum value of u. So what is the u max you will get from here also. Okay, so from here also you will get the maximum value. So that means you will get the response, you draw it. So you have the expression of displacement. Now from here you will get, you can draw this response, and from here you will get the what is the maximum value. Now, one more thing that I want to discuss, that I have got this, I have discussed the two cases. Now, you can discuss similarly, you can get the response from other cases also. Now, the thing is that from here, how I will get the response spectrum for real earthquake. Okay, so what I will do, that the response spectra is what is given, that it is you can see the maximum values of acceleration, velocity, displacement, that depends on natural frequency and damping ratio, that we have shown. That here in the example problems I have not considered damping ratio, but you can consider damping ratio also, that those expressions also I have given. So now the thing is that the maximum values of acceleration, velocity and displacement are referred as spectral acceleration, spectral velocity and spectral displacement. Okay, and then the expression of acceleration, velocity, displacement, time history can be obtained by using Duhamel integral. So I have discussed what is Duhamel integral also. So here I have used a simple harmonic type of base acceleration. I will get the expression for displacement. Okay. Now, if you have a real earthquake type of loading, which, and then for any arbitrary loading, you can get the response by using this expression, by using the Duhamel integral that I have discussed. So that means you will get the expression for displacement, velocity and the acceleration. So if you have that expression for displacement, velocity and the acceleration, then from there you will get the maximum values of displacement, acceleration and velocity, and that you plot for different time period, then you will get the response spectrum. Okay. So now if I give you the example, that suppose if you have a say a building whose your T0 is say T01, that means whose natural time period is T01. I have discussed that if you change the stiffness in my previous example, then your T0 value will also change, then your maximum deflection will also change. Suppose in any of the expressions that you change the T0 value, then you will get the different maximum deflection. So here also, suppose you have a structure whose T0 is T01, then you apply that earthquake motion for the, and then you will get the displacement response, like the way I got the displacement response for the simple case. So you will get the displacement response, and then you will plot. In previous case also I have plotted the response, displacement response. So that means in a structure whose T0 is T01, you plot it, the response. So this is, you say ut and you plot it with t. Then you, if you have the, so this is a displacement response. So from here you will get the maximum value. So this will give you u max 1, or you can take the mod actually, because it is maximum value. It can be negative or positive also. So this is your u max 1 you will get. Similar way I get the u max 1. Say. Okay. So this was also u max 1. So I will get the u max 1. Now what I will do, now I will apply the same motion to another structure whose T0 is equal to T02, a different natural time period. So then I will get the again a different response for the deflection. Okay, so different response for the deflection. Say I will get this type of response. For example, from here I will get the again u max 2. That can be up, that can be down also. It's not, it can be positive, it can be negative also. It is not always that it can be say positive, it can be negative also. Here this can be u max. Okay. So now I will get another structure. I will say whose time period is T03. Then I will apply the same motion, same loading, earthquake loading, and I will get the deflection response or displacement response. Okay. So suppose this is my U max. This is 3. So now different time period I will get the different maximum value of displacement by using the same response or same ground motion to different structures, okay, on similar type of soils and for a particular damping ratio, okay, because it is a function of time period and the damping ratio. So you fix that damping ratio same, and then you change the T0, and then you will get the maximum value. Now that maximum value will give you, that maximum value is the spectral displacement. Okay. Now I will plot this spectral displacement curve is D, and with T0 or frequency. If you know the time period, you will get the frequency T0 or frequency. So then, so suppose for this is my T01, this is T02, this is T03, and so on. Now this is my SD. So from here T01, what is the maximum? This is my U max 1, say. So this will be, say, U max 2. This will be U max 3 that I will get from these responses. So this will be 1 point. This is, say, another point. This is, say, another point. Okay. So I will get, say, this type of response. Okay. So from here, say, I have these different points. So similarly, in between that also I will get different time period, natural time period, then I will get this plot. So this particular plot is then, it is called as displacement response vector. Okay. So then how I will get the Umax? I have given you the example problem where I will get, you get an idea for simple case how I will get the Umax for different time period. For now, if you apply a real earthquake motion for different, for structure with different time periods, and then if you get the response or of those velocity response of those cases, then you will get expression of your displacement, and then you plot them with time for different cases. From there you will get the maximum displacement. Now that displacement will plot with respect to time period or frequency, then you will get the displacement response vector. Okay, then, and keeping say at any constant damping ratio. Here, say, damping ratio, for example, say it is 5%. Okay. Now for different damping ratio also you can derive similar type of response spectra. So now similar way, if you have the you can develop the expression for acceleration, you can develop the expression for this velocity, then also you can get the your different spectrum, that is the acceleration response spectra plot, then velocity response spectra plot. And then I have also discussed that from the Umax how if you you will get the your from velocity response spectra from here SD, then how will get the SV by multiplying that omega that I have discussed, then you will get the SA also. So that means you and in that case for any earthquake loading you have to take the help of the Duhamel integral, so to get the expressions for acceleration, velocity and displacement time is t. Okay, and then from there you will get the maximum value, and then that you plot, you will get the your acceleration response spectra, velocity response spectra and the displacement response spectra. So this is your that acceleration, velocity and displacement response spectra for different two sites. And I have already discussed that for the design response spectra, you see it is basically the average of several earthquake motion. Here I have discussed it is only for one earthquake motion. Such type of response you will get for under several earthquake motion, and then you will get the average of those things. You will get the, this is SA by G, your basically response. This is design response spectra. From there ultimately you will get the lateral force or the earthquake seismic force or the other required forces that you need, you will get from that response spectra curve. From there you will get the SA by G. So that is your design acceleration coefficient for different types of soil, and that can be used to determine the design horizontal seismic coefficient, and finally the design lateral force or the seismic force that is acting on that particular structure. Next class I will discuss that how I will use those attenuation relationship, and then I will get my required ground motion parameters, say PGA or PHA or velocity in the next class. Thank you.